Hello, multivariable calculus students. This is Mr. Johnson, and this is the second video for section 9.6 on surfaces, and we're going to talk now about the graphs. So in the first video, we talked about the domain and the range, and then we also talked about sketching the domain. So now we're going to talk about the actual surface itself, and we're going to look at a couple basic surfaces, and then I'm going to show you a chart that kind of goes through some of the main ones that you'll be looking at and dealing with. And again, keep in mind that this is just an introduction, and we're going to work on these a lot more. We're going to basically spend entire chapter 10 studying these types of surfaces and the behavior behind them. So if it's a little overwhelming to look at some of these, just bear with me, kind of work through them, and they will get easier with time. So the first example we're going to look at is the sketch of the graph, the linear function given by f of x, y. And keep in mind, I just want to warn you that I'm not going to be testing you on your ability to sketch these three-dimensional shapes. So when we're sketching things, we're trying to visualize things, I want you just to get an idea behind it. And I want you to also use your technology. I want you to use your iPad, or you can use some other technology online as well if you'd like to research some of that. I've provided basically all of these images for you just because, again, the idea here is to get the sense of what the equation gives us, not to come up with some, beautiful artistic rendering of the image itself. In this case, you can see that the intercepts are defined over here in our graph, and the intercepts would be, if we're looking at the x-intercept, we're going to let both y and then z be 0 and get 2 and so on and so forth. We actually, if you remember back to a previous section, we ended up studying this particular function. I'm going to rewrite this as z equals 6 minus 3x minus 2y. And the reason I'm going to do that is that I'm going to rearrange it slightly and see if you notice what type of surface this is. You could even rewrite it like this if you'd like. This should look really familiar to you. This is the equation of a plane, and we studied this form of the equation of a plane, this linear form of the equation of a plane, in section 9.5. So I hope that helps. If just as a quick review, the normal vector is 3, 2, and 1. Okay, so we have a plane, which again we studied in 9.5, but now when we start talking about surfaces, a plane is of course a surface, and it's one of the more straightforward, kind of simple surfaces. But just keep in mind that that's kind of the introduction that we've taken along the way here, is to start with a plane. Let's talk about the next one in example 7. So you can see the shape that's formed over there. And I guess the question is, okay, let's think about why that shape is formed. So remember, this is really z equal to x squared. And since we don't have any y value in our equation, y can vary independently. Y can be anything you want it to be. So let's say that, I don't know, let's let y equal 0. Okay, well, then our graph is z equals x squared, and it is on the xz plane because y is equal to 0. And what we end up getting is, in our sketch, we get this little, this is called a trace. We get this trace, this little sketch of that particular parabola on the xz plane when y was 0. Now, if you let y be, let's let y be 3. Well, we get the exact same thing. We get z equals x squared. It's not on the xz plane. It is parallel to the plane, but it's now moved off just slightly, and maybe that's right here on our particular sketch over on the right side. So what you can see is that no matter what y is, you're going to get this parabolic shape over and over and over and over again. And if you put all of those little parabolic shapes together, all those parabolas lined up, you end up getting this little infinite u in both directions along the y-axis. I included a sketch of the GeoGebra because I think it does a much better job of showing where this is coming from. You can see all of these little parabolic shapes forming along the y-axis over and over and over and over and over again. And obviously, if you continued that process, it would just fill in perfectly, and that's where this shaded surface comes from. Okay, so that's going to be another type of example we'll see in which maybe one of the three variables does not show up and therefore it varies infinitely, which causes you to have maybe a shape that you're used to in single variable calculus on a plane. So for instance, in this case, a parabola. You're used to seeing a parabola, but now in space, all of a sudden, if one of the variables can vary, now it looks like this infinite looking parabola. Okay, let's go on to the next example. All right, so in this example, we're going to talk about what's called traces or cross sections or slices. Basically, what's happening is that when we start to visualize a particular surface, it may be helpful to think about it kind of like what I was talking about in the last one, where we let one of the variables be a constant. So we let that sort of not vary anymore, and we look at what happens to the other two variables, how they interact, what shapes they form, and then we sort of put them together. I don't know if any of you did this in elementary school, but I remember when I was a kid, when I was learning about, early elementary school, we would have colors and we'd have shapes and different things. And back in the day, this is going to date me a little bit, but we had the overhead projectors and all of that. And some of you know what that is, and others of you have never seen an overhead projector. But an overhead projector would just basically project whatever image is on the base of the machine up over into the front of the room on a projector screen. And I remember my teachers in elementary school would have those different colored tiles, yellow and green and blue and all that. And we would start to overlap them and see the different colors that formed and things like that. That's sort of what I think of this. So when we trace out this function and we come up with like these little individual pieces, I think about what if we were to put those overlapping each other, what object would it end up forming? And that's really the goal behind trying to visualize this three-dimensional shape is to overlap all these different pieces together to form the object. So in this particular case, what we have is the function z equal to y squared minus x squared. And I'm not going to show you every single trace because there's a lot there. And over in the set of or the portion over here on the side on the right, you can see all the different traces. I'm just going to walk you through where they really came from. So let's take a look at, let's say that we want y to equal k. So in other words, we want to perform a trace where y is this constant value, and that would mean that we are going to be on the xz plane for when y is equal to some value k. So our equation then is z equal to k squared minus x squared. So let's say we want to let k be 1. Well, that would give us z equal to 1 minus x squared. Now, I know it's z, so that can be a little confusing, but it's just on the z axes. So think about what would the equation for z equals 1 minus x squared look like? Well, it has a vertex at 1, and it's an upside down parabola opening downward, which would be represented over here in this middle sketch right there, that little parabola that's formed. Now keep in mind that if k was -1, you would actually get the same thing. That's why they're notating that's positive or -1. Let's say that you have k equal to 2. Let's do -2. Then you would get z equal to 4 minus x squared. Well, that's going to be in our sketch right here. Of course, that's the same thing as +2 because you're squaring that. Now, if we were to let, let's say, x be k, and you can see all of the information up here, if x is k, well then you're going to look at traces along the yz plane, and all of those are going to be right here. Those are going to be just parabolas opening upward. And then, of course, you have your other traces over on the right side where z is equal to k. Now, when we put all of these together, and that's what I do like this visual right here, when we kind of put them all together in space and we start to combine them visually, we end up getting this sort of saddle graph that you can see here, and is formed by all of these separate traces. I've included the GeoGebra sketch over on the left side of my screen just because I feel like the GeoGebra sketch is really nice. You can start to see, like for instance, this parabola that we just analyzed there where k was equal to 1. And then we have this other parabola. Here's k equal to -2 right there. And then this one you can't see very well, but this would be k is equal to +2, and so on and so forth. You can see all these traces that are formed and how those traces then build the entire surface. Example 9 is actually one of the ones that we had done at the beginning of the section where we were looking at this paraboloid. And so I had mentioned in the GeoGebra rendering of this that you can see these parabolas forming, all these different parabolic shapes. You can also see that there's this ellipse looking shape as well. So I'm just going to show you where those come from. Okay, so let's say that first off we have z equal to 4x squared plus y squared. So let's say that z is equal to a constant value k. So what we would have if let's say we want to let k equal 1, then we would have 1 equal to 4x squared plus y squared, and that's an ellipse that's forming in this paraboloid there. And again, let's just pretend like it's right here. Okay, that's what would be forming in terms of a trace. If we let k equal 0, then we would get 0 equal to 4x squared plus y squared, and that's going to be actually your vertex right here where z is 0. Okay, let's say that you want to let, let's do x is equal to k. So then we would have z equals 4 times k squared plus y squared. So if we were to let k be 1, we would get z equal to 4 plus y squared. So then we start thinking about what that may look like. Now remember, this is on the YZ plane, and that's going to be a parabola then that has a vertex of 4 opening upward. And again, if you look over at the GeoGebra sketch, you can see this a little bit better, although our scale is not as good, just because it only goes from -5 to 5. But you can start to see those parabolic shapes then forming along this paraboloid. So what's happening with traces, again, is that we're trying to kind of simplify down the surface and look at just different portions of it. If one of the three variables is then kept constant, what shape would we be looking at on a plane? Okay, we're going to move on to the next page where I'm going to show you some of the different shapes that you're going to see in class. Now this is one that is taken from an online text that I found over the years, and it goes through a handful of different shapes. The thing I like about it is that it sort of tries to break down, different elements of the equations. You have your ellipsoid, you have the cone, that kind of thing. You can read through these. Again, it's helpful information. There is more here than what you need to know for class, which I'm okay with. So I'm kind of erring on that. So I want to make sure that you have more at your disposal in terms of learning this material. I'm going to go on the next page. This is the chart that is in our textbook, and I think it's good as well. One of the things I do like about it is that the pictures are nice and clear, and some of the descriptions are very specific, and it kind of walks you through certain elements of the equation that are important. So for instance, the information about the paraboloid we're going to discuss in just a moment. It says the variable raised to the first power indicates the axes of the paraboloid. So if z is raised to the first power, then the axes for the paraboloid is z. If it was x that was raised to the first power, the axes would be x, which means that paraboloid is sort of on its side there. You can look at that in some of the other surfaces as well. So I encourage you to just review these. You do not need to make a note card right now of quizzing yourself on each one of these. I just want you to know that this is a resource right now, that you can utilize it as a resource, and we will continue to work on it, especially as we begin chapter 10. So this is an overview. Please don't stress about all of these surfaces. Some of you have seen them before. Some of you haven't seen them very much at all. just I want you to start to become familiar with them. And if you start to see an equation, I'd like you to start to try to figure out, okay, what type of equation is that representing? What surface is that? Okay, I'm going to show you an example of this, and this one's a little bit more complex, which is okay, but we want to classify the surface. I do have it written for or shown to you in graphical form right now, but one of the things that we can do with this one is we can complete the square to get a better sense of what's going on with it. We have, I guess, kind of to rearrange some things really quickly. So I'm going to do this. So what I'm doing, actually, hold on here, back up. This is equal to y, and then I'm going to subtract 10. So what I'm going to do is take x squared minus 6. I'm going to add 9 to complete the square, and that means I'm going to add 9 to the right side to balance the equation. So I'm tweaking it a little bit. This gives me x minus 3 squared plus 2 times z squared, which is equal to y minus 1. Now you may be asking, okay, why in the world am I doing it in this type of way? Well, again, we have our paraboloid that's drawn over here on the right, but aside from that, if we were to look up at the elliptical paraboloid equation, you can see that we have a situation that's kind of similar to it. Now, we could scale this a little bit. So for instance, the z squared element, we could be dividing that by 2. We could certainly do that now if we'd like. I'm not too worried about that element right now. What I'd like to focus on a little bit more is where the axis is for this paraboloid. And so if we look back on that description that's up here, it says that the variable raised to the first power indicates the axis of the paraboloid. So if we notice this paraboloid, we should be able to determine that it does open towards positive y because y is the variable raised to the first power. But also, we know when we studied circles and things like that in higher algebra and pre-calculus, we know that the factors of the equation are going to indicate the vertex. So for instance, we have x minus 3, which means that the x value of the vertex will be 3. We have z without any factor there, which means that the z value is going to be 0, and then y would be positive 1. So we can actually, from this equation, we can pull out this vertex 3, 1, 0. We know that the form of it is essentially the parabolic form, and we then also know that it opens towards that positive y simply because y is to the first power while the other two are squared. Now all of a sudden, if this plus sign was a minus, well, now we may be looking at the hyperbolic paraboloid instead. But again, those little differences are important to just at this point dig into a little bit and explore. But don't be stressed out about the level of it yet. That's going to come a little bit later in chapters 10 and 11. So right now, I just want you to get an idea, have these charts handy so that you can look at them and reference them. And that is it for us for section 9.6. Thank you.